So now we are on section 3.5, which is talking about implicit differentiation. And so far in the context of differentiation, we've been thinking about y and x as being two variables related to each other by a function. That is, y is equal to some expression in x. However, that's not the only way that we can get relationships between two variables. It doesn't always have to be y is some expression in x. For example, we could start with just some equation in x and y. And then from there we can get the solutions of that equation and they form some sort of graph. That gives us a relationship between the variables x and y. But typically this sort of thing is not going to be a function. For example, if I look at the equation x squared plus y squared is equal to 1, that gives me the unit circle centered at the origin, just like this. And it fails the vertical line test pretty poorly. For most vertical lines between -1 and 1, it hits the graph twice. Not a function. So can we still apply calculus to something like this? Well, first let's talk about why we might be interested in applying calculus to something like this. So for example, let's say we're looking at a particle moving along a circular path at a constant speed. Well, speed is just talking about the absolute magnitude of how fast you're going. But if I want to talk about velocity, I need to know more. Velocity is actually not just the speed, it's also the direction. It's not just the magnitude of my change of motion, it's also the direction in which I'm going. When we're doing one dimension, we've seen that velocity can be positive or negative. If we choose one direction to be positive, the other to be negative. In two dimensions, all of a sudden we're actually talking about different sorts of directions that something can be going in the plane. Okay, so what is the direction of velocity when we're talking about a particle moving around a circular path? Well, it turns out that it's going to be the tangent line to the circle at the point wherever the particle is at the moment. So the velocity of the particle at this point right here has magnitude equal to whatever the speed is, but its direction is tangent to the circle. And we need to understand this to be able to do physics sort of problems. So here's one application where I need the tangent line to a curve which is not a function. Here's another example. So in cryptography, we would like to take a message and scramble it up somehow, send it to somebody, and then allow them to unscramble it. Well, one way we can do this is to represent data as points on something called an elliptic curve. For example, y squared is equal to x cubed minus 2x plus 4. What does this graph look like? It looks like this black curve right here, and you can see that it fails the vertical line test. It's not a function. However, we are interested in finding tangent lines here. Why? Because when I take 2 points on an elliptic curve, it turns out that there's a notion of addition on the elliptic curve. What I do is to add points P1 and P2. I draw the secant line that connects them. And by the algebraic properties of the elliptic curve, there's always going to be a third point that it hits. Well, the sum of P1 and P2 is not going to be this third point for a technical reason. It's going to be the reflection of that point about the x-axis. But still, to get P1 plus P2, I need the secant line, and then I find the sum of the 2 points. What do I do when I want to add a point to itself? It turns out that the right thing to do is to take the tangent line. I take the tangent line at the point P, and that will always hit the curve in a third point. Then I reflect that about the x-axis, and that will give me P plus P. So, in order to use this encryption system in cryptography, I need to be able to add a point to itself. That requires being able to find the equation of a tangent line at any point on this curve. Now, to apply calculus to these equations that give us curves in the plane, we really need to be able to think of them as functions. But we've seen that generally they're not going to give us functions. What can we do, though, to get away from the fact that these aren't functions so that we can actually apply calculus? Well, what we can do is we can actually cut up a curve into pieces that do satisfy the vertical line theorem. So, for example, let's take the unit circle at the origin, x squared plus y squared is equal to 1. Well, if I cut this guy up into the top semicircle and the bottom semicircle, so over here I've got the green top semicircle and the blue one, all of a sudden I've got two curves that pass the vertical line test. The green guy in and of itself passes the vertical line test. The blue guy in and of itself passes the vertical line test. So I can really think of this curve right here as being two functions. Now here I can actually explicitly solve for these two functions. The top is going to be y is equal to the square root of 1 minus x squared. The bottom is going to be y is equal to negative square root of 1 minus x squared, just solving for y. But we can't always do that. We can't always explicitly solve for y. Okay, so let's consider the equation x cubed minus x squared y minus xy squared minus y cubed plus y equal to 0. If you plot the solutions to this equation, you get this sort of S-looking curve right here, and this really fails the vertical line test. Well, the y-axis hits it in 3 places, so it fails the vertical line test. But I can cut this guy up into 3 pieces that each satisfy the vertical line test. I can take the top piece of the function, or the graph, which is blue right here, the bottom piece right here, which is green, and then this middle piece I've made red. Each of these 3 pieces gives me a function. So yeah, I can consider this curve to be a y to be given by 3 different functions of x. Now, can I sit down and actually try to solve this for y? It turns out, yeah, you can solve this for y, but let me show you what happens if you try to do that. So I plugged this equation into actually Wolfram Alpha and I asked it to solve for y, and it spat back 3 equations at me. I'm pretty sure that this first equation that it gave to me is the red piece of the curve. Y is equal to this, minus x over 3. Yikes, no. This is not going to be the right way to attack this problem. First of all, you don't know, I don't know how to do this. Second of all, even if we did, this would be absurd to try to sit down and take the derivative of. So really, we need some other way to be able to take the derivative of an equation like this. Let me just give one more example of why we need some other sort of way of differentiating equations like this. This right here is 2x to the 5th minus 2xy squared minus y cubed minus y equal to 0. When I graph out this equation, I actually do get the graph of a function. It's not bad like the other things that we've been looking at so far. It is a perfectly fine function because it passes the vertical line test. But some guys way back when showed that equations like this, you actually cannot, you literally cannot, it's literally impossible to solve for y as an algebraic equation in x. There is no way of doing it. You could sit down and try to do it. It's never going to happen. No way. So we literally can't write y equal to some sort of function in x involving algebraic expressions. We literally need to treat this function differently using some other technique. So this is going to be called implicit differentiation.